Hypothalamus Artificial Intelligence, HAI. Digital transformation powered by real-time autonomous and intelligent algorithms. Presents the Conference Oil Lubricant Blend. Nonlinear Optimization. The material of conference was organized by the engineer Jesus Velasquez Bermudez, Ph.D. This conference is based on the paper Multi-Objective Optimization Model of Industrial Lubricants based on Integer Nonlinear Programming. Industrial lubricating oil is a liquid or semi-solid lubricant used in various types of automobiles and mechanical equipment to reduce friction and protect machinery and machine parts. It mainly plays the roles of lubrication, auxiliary cooling, rust prevention, cleaning, sealing, and cushioning. At present, the demand for lubricating oil shows a trend of specialization and customization. Different mechanical equipment and applications have different requirements for lubricating oil performance, so there is an urgent need for enterprises to produce specific quality lubricating oil according to the actual demand. Lubricating oil products are prepared by mixing two or more base oils with different properties according to a certain proportion. However, the varieties of base oils refined by oil refining enterprises are limited, so it is necessary to use limited base oils to prepare the required lubricating oils. Therefore, the blending of base oils is the basis for the preparation of lubricating oil products. The most common method of lubricating oil blending is tank blending. The image presents an oil lubricant production plant. The image presents the base oil supply chain. Oil lubricant blend and nonlinear optimization process. The physical and chemical properties of oil products change when they are blended. The linear or nonlinear relationship between this change and the properties of each blending component is expressed as an additive effect between the components. A certain physical and chemical property equal to the superposition of each component according to its composition ratio is called linear harmony, otherwise, it is called nonlinear harmony. The chemical composition of oil products and additives is very complex, and their physical and chemical properties generally do not have an additive effect, so the blending of lubricating oil is mostly nonlinear. In addition, the performance indexes of lubricating oil mainly include viscosity, freezing point, acid value, flash point, oxidation stability, residual carbon, and so on. Therefore, the optimization of the design of a lubricating oil blending scheme mainly includes two aspects. To select the base oils reasonably to meet the performance index requirements of the blended product, and to establish the blending mathematical model, and determine the blending scheme of each base oil, on the premise of meeting the product performance indexes. The blending formula of early lubricating oil was mainly optimized by the linear programming method. However, many important technical indexes of lubricating oil do not show a simple linear relationship with the content of each component. If the oil products are blended according to the linear programming method, the prediction accuracy of the performance of the blended product will be poor, and unable to meet the actual needs of production. The nonlinear programming method can manage the nonlinear relationship between important indexes of lubricating oil, and the content of each component, and have obtained many accurate prediction models. Then, the blending of lubricating oil is a relatively complicated process. The next model ignores the production technology and the process of lubricating oil, and does not consider the issue of additives. Considering that a certain index of lubricating oil is only related to the corresponding index of the base oil, it is necessary to optimize the design of the blending scheme, so that it meets various performance indexes and, at the same time, is lower in cost. In this paper, a multi-objective optimization model of lubricating oil, based on integer nonlinear programming is presented. The proposed modeling process considers two stages. First, data preprocessing, and second, optimization of the blending. The first is based on predictive analytics and the second on prescriptive analytics. Data preprocessing. To manage nonlinearities and uncertainty in the transformation functions of the mixture of the base oil characteristics and the technical specifications of the lubricant, the following process was followed. 10 base oil was considered. The performance indexes considered are viscosity, freezing point, acid value, flash point, oxidation stability, and carbon residue. The production data of 20 batch of blended base oil was captured. For each batch was established the value of performance index, in the appropriate measurement units. The data was normalized for the 20 batches, to calculate the mass fraction of base oil in each batch of blended oil. The calculation formula is as follows. The mass fraction matrix of blended oil is equal to the mass of base oil I in batch J of blended oil, divided by the total mass of batch J of blended oil. The table presents the value of the performance indexes for each of the base oils considered, and unit costs per ton for each base oil. The table presents the composition by weight of each base oil in each batch. From this data, the mass fraction matrix is calculated. The table presents the observed index performance for each batch. All the above data will be used to calibrate the contribution formulas of each base oil in the blend for each performance index. In this paper, the viscosity of each oil batch is calculated using the internationally common viscosity blending calculation formula. For the freezing point, a polynomial formula is proposed. For the other indexes, acid value, flash point, oxidation stability, and carbon residue, the linear blending formula is applied to predict the lubricating oil indexes. The indexes with low prediction accuracy are adjusted non-linearly, and, finally, the blending scheme uses a complex power polynomial for high-precision prediction. Adjusted data for viscosity. Viscosity is one of the most important characteristics of lubricating oil and a performance index that should be considered first in lubricating oil blending. In addition, the viscosity of lubricating oil is an important basis for classifying oil brand numbers. The viscosity calculation formula is established as follows. The logarithm of the observed viscosity is equal to the sum over the base oils of the mass fraction of the oil mixed, multiplied by the logarithm of viscosity of the base oil. The relationship between the calculated viscosity value and the measured value of each batch of blended oil calculated is shown in the figure. The calculated value is in good agreement with the measured value, and the error is 0.002%. Therefore, the calculation formula can be used directly. Adjusted data for freezing point. The freezing point calculation formula is established as follows. The calculated freezing point value of batch J of mixed oil is equal to the sum over all base oils of the mass fraction matrix of the mixed oil, multiplied by a polynomial function of the freezing point of the base oil. The polynomial function includes two factors that must be estimated, h and f. It is equal to the freezing point of the base oil raised to the power f, plus h multiplied by the freezing point of the base oil raised to the power 1/3. Using a nonlinear least squares algorithm, the values of f and h are 0.4754 and minus 0.003, respectively. The calculated value is in good agreement with the measured value, and the average error is 1.546%, so the calculation formula can be used directly. Adjusted data for acid value, flash point, oxidation stability, and carbon residue. The standard formula for linear blending is used for a general calculation formula for the acid value, flash point, oxidation stability, and carbon residue. The image shows the curves of the four indices. Multi-criteria blending optimization model. In the actual production of lubricating oil of specific quality, it is often necessary to consider both cost factors and performance factors. Based on these, this paper establishes a bi-criterium objective function, composed by two measures of success: economic value, cost of the base oil, and relative error value of the performance indexes. The objective function is equal to the weighted sum by the WP factor of the sum of the costs of the base oil, plus the weighted sum by the WQ factor of the sum of the absolute error value of the indexes. Multi-criteria optimization is a branch of optimization, very studied and widely used to face mathematical problems in which the decision maker has more than one criterion to select the objective function. In this case, two criteria may be considered: cost of the base oil, and error value of the performance indexes. Normally the criteria move in opposite directions. If we optimize one criterion, the other is de-optimized. The formulation of the objective based on subjectively weighing the conflicting criteria has a fundamental problem. The solution of the problem depends on the decision maker criteria, which is not desirable. In this case, it has that for any feasible rational solution, there will be a pair of weights, WP and WQ, that produces such solution, which decreases the benefit of optimization. On the other hand, if there are subjective variables in the objective function, the solution also depends on the measurement scale of these variables. This implies that if it changes the scale of a variable, it is this case K, the solution changes. This is not desirable in an optimization model, as it allows the decision maker to manipulate the solution of the mathematical problem. The best way, in the opinion of the speaker, is to build Pareto curves of the two criteria, and based on its analysis make the decision. The image presents the additional constraints that must be included in the mathematical model proposed in the paper. Unfortunately, there are problems editing the restrictions formulated in the paper. For this reason, an adjusted model is presented, with the corrections that the speaker considers should be made. Constraint conditions were established by the following. Weight of the mixture, tons, defines the weight of the mixture to be made. Control of the amount of base oil, tons, determines that the amount of base oil to be used is multipliers of Z0. Error handling, limits the error for each performance index to a maximum value equal to delta. Calculation of the error based on the control batches, determines the error of the index, taking as reference the control batches, and budget control, determines that the total unitary cost of the mixture is less than a certain cost R. The second constraint, the control of the amount of base oil, makes the problem discrete, MIP, mixed integer programming. And viscosity and freezing point constraints make the model nonlinear. The resulting problem is MIN-LP, mixed integer nonlinear programming. Solution and analysis of nonlinear programming model. A customer requested 80,000 tons of lubricating oil at a cost of no more than 3,500 Chinese yuans per ton, and with performance indexes as shown in table, the error of each index is no more than 5%. In the corresponding constraint conditions, the total mass G of the base oil in the blending oil scheme is 80,000. To ensure that the quantity of base oil is adjusted to an integer multiple each time, the value of Z0 is 100. The maximum type of value of the base oil in the objective function corresponds to 10, the maximum type of the blending oil index corresponds to 6, and the maximum type of control batch is 20. The paper presents three blending schemes for different factors of the weights of cost and performance. Mathematically, they are characterized by the value of the criteria factors. WP weight of the economic value, WQ weight of the relative error value. The schemes are, economic value, cost of the base oil. Weights, WP equals 1, WQ equals 0, relative error value of the performance indexes. Weights, WP equals 0, WQ equals 1, and mixed scheme. Weights, WP equals 0.5, WQ equals 0.5. The table summarizes the three schemes considered. The blending schemes are shown in Table 5. The composition of the optimal mixture for each of the three optimization schemes is presented. The blending schemes are shown in Table 5. The calculated values and required values of each index, and the cost of each blending scheme, are compared in Table 6. According to the Table 6, all performance indexes of Scheme 1, performance error criterion, meet the requirement that the relative error does not exceed 5%. At the same time, the cost is $3,453.25 per ton, which is lower than the 3,500 Chinese yuans per ton. All performance indexes of Scheme 2, economic criterion, meet the requirement that the relative error does not exceed 5%. The cost is $3,075.96 per ton, which is lower than the $3,500 per ton, required by the customer, and far lower than the $3,453.25 per ton of Scheme 1. However, the relative errors of all performance indexes except Index 2 are close to 5%, which is unfavorable to the overall performance of the blended oil. According to Table 6, the cost required by the customer is less than $3,500 per ton, so all schemes meet this requirement. In this research work, if more attention is paid to the performance index factors, then Scheme 1 is recommended. If the cost factor is more important, then Scheme 2 is recommended. If the cost and performance index factors are considered, then Scheme 3, mix of economic and indexes performance recommended. It is important to note that if the units of measurement of the variables, of any type, are changed, the solution of mixed Scheme 3 changes. Multi-criteria optimization and Pareto optimal decisions. Pareto efficiency, also known as Pareto optimality, is a concept of economics, which has applications in engineering and in different social sciences. The term is named after the Italian economist Vilfredo Pareto, who used this concept in his studies on economic efficiency and income distribution. In the case of multi-criteria optimization, if given a criterion assignment, a shift toward a new assignment, which at least improves one criterion, without making the situation of the others worse, is called Pareto improvement. An assignment is defined as Pareto optimal when no new Pareto improvements can be achieved. In this case, there are 6 lubricant quality criteria. To facilitate the explanation of the analysis of this case, only 2 criteria will be considered. The viscosity indicator criteria will be the criterion 1, and the criterion 2 will be the cost. The optimal Pareto points configure the Pareto curve of a multi-criteria problem. For the case of 2 criteria, the process of constructing a Pareto curve is as follows. First, solve the problem optimizing only criterion 1. Second, solve the problem optimizing only criterion 2. The values of the objective function for the above cases define the extreme points of the curve. Subsequently, the problem is modified by including as a constraint a bound for criterion 2, and the criterion 1 is optimized. The bound will be higher if the best thing for criterion 2 is to maximize it, and lower otherwise. The modified problem is solved multiple times, for various criterion 2 bounds. Normally, choosing values that move from the best bound of criterion 2, to the worst. Depending on the senses of optimization, the curve must be convex or concave. In this case, the curve must be concave. In the case in reference, the extreme points of the Pareto curve are point 1, 3,500 to 30.64, and point 2, 3,075 to 39.12. Between point 1 and point 2, there are infinite numbers of curves that can join them. To know the proper shape of the curve, experiments must be performed to obtain curve points between the 2 extreme points. In the case of a study, an experiment is carried out with the factors WP equals 0.5, WQ equals 0.5. These factors are arbitrarily selected. The idea may be to generate information about the shape of the curve. But in this case the scheme 2 produces an unexpected result, a better solution for the viscosity index. That implies that the maximum obtained by the scheme 1 is not the optimum value. This can be explained by the nonlinear nature of the problem which, being non-convex, requires a global optimizer. In this case, the technology used was Lingo's Generalized Reduced Gradient (GRG) algorithm, which is oriented to convex nonlinear programming, this without considering the discrete constraint, which turns the problem into a min-LP. Then, the optimal Pareto curve is not coherent. The lecturer prefers the method described above for constructing the curve, using multiple experiments between the extreme points of the curve. Implementation of the mathematical model. Regarding the implementation of the methodology, it should be considered that the process must include 2 types of modeling. Predictive analytics, oriented to the estimation and validation of the quality characteristics of the base oil. In summary, forecasting of the quality of the base oil, and prescriptive analytics, oriented to the optimization of the base oil blending process. The implementation of models based on predictive analytics involves the selection of one of the following methodologies. Data-based methods. These methods try to identify the parameters based only on the data, without considering the equations of the physical process. The most known methods are artificial neural networks, ANN, support vector regression, SVR, and advanced probabilistic methods, APM. Model-based methods. These methods try to identify the parameters based only on the equations of the physical process, without considering the characteristics of volatility of the data. It includes physical process based on differential or algebraic equations, and parameter estimation based on ANN, SVR or APM. Hybrid methods, dynamic methods that combine multiple data sources, the sample volatility, and the certainty about knowledge of the physical process, or its modeling. The most known and used method is state estimation, mainly the Kalman filter. Regarding data processing, it must be considered that base oil must be acquired, or produced, in batches. During its lifetime, these moments should be considered 2 stages. the time of its arrival or beginning, to be used in production, and the use of base oil in the production of multiple batches of different lubricants. From the point of view of the parameters estimators of the predictive model, two stages, related to the previous ones, must also be considered. Initial estimators and re-estimation of estimators. The ideal is to test the base oil, in the production of multiple test batches, and from there make the appropriate initial estimators. This before the formal production. If this is not possible, for whatever reason, the solution may be to establish an additional model, to estimate the initial estimators from the existing information for other base oils. During the second stage, multiple batches of lubricants produce data, to verify that the initial assumptions over the base oil are appropriate. An alternative model is proposed based on a formulation that minimizes production costs and guarantees lubricant quality restrictions. The model includes all the typical constraints of a blending model. It should be considered. To consider nonlinearities due to viscosity and freezing point, the FOBO function is used, y. And the factor f-seg, safety factor in quality, a fraction, is introduced. To perform a multi-criteria analysis, this problem can be solved parametrically for different safety factors values, to construct a cost versus f-seg Pareto curve. The previous mathematical model can be extended, to become a useful model at the level of real cases. Among many, the following constraints can be considered. Time windows to meet lubricant demand, additives must be included to improve or stabilize quality conditions, multiple types of lubricants are produced simultaneously, multiple types base oil may be used, and scheduling to receive the base oils, may be in ports or in terminal of the pipelines. The model may include restrictions on facilities, for example tanks, and include the time, to convert it into a dynamic model. Like Herbert Simon, hypothalamus artificial intelligence believes that the computer-based mathematical modeling is the greatest invention of all times. Thank you for your attention.